So in this second problem, we have a tank of water that starts off already 30 centimeters full, and we turn on a pump to gradually fill it more and more and more, but it only fills up eventually to getting closer and closer to 54 centimeters. Presumably this is based on the strength of the pump. The pump can only support up to 54 centimeters worth of height. So we're transitioning from starting 30 centimeters full and approaching 54 centimeters full. And just based on that alone, what should we expect the graph to look like? Does that tell us anything about what we can expect the graph to look like here? Like if we were making a graph of height versus time. What value do we start at? Yeah, we're starting at 30. We should expect exponential decay towards what asymptote? What should we expect the height value to approach after a long time? Yeah, it's going to increase towards 54. So we can assume this is exponential decay starting at 30 and approaching 54 as an asymptote. So if we fill in the asymptote, and we know we're starting at 30. So we've got one data point at least. We also know after 23 minutes, it's going to be at a depth of 53. So that might give us a little more detail. But in general, we should expect some sort of exponential decay curve, getting closer and closer to the asymptote, but never quite reaching it. However, we don't really know how steep that is. Maybe it decays really quickly. Maybe it decays much more gradually. We do have the one data point of at 23 minutes, the depth is 53. So we at least have that one more data point on it. But to get any more information in a useful sort of way, we're going to want to, we'll want to write an equation for this. So how could we write an equation for this? What should we generally expect an exponential decay function to look like? First of all, what's the most basic, simple, foundational exponential decay function you can write? I would go even simpler than that, without any parameters at all. I think the simplest exponential decay, I mean, it's exponential, so it's got to be e to the something. And if it's exponential decay, what should we assume about the exponent? Then note that this graph is not a value that's decreasing, though. This value, the height, is increasing. We still consider it exponential decay, though, because it's getting closer and closer to the asymptote. However, if I just write e to the t, that's not going to be exponential decay. What has to be true about this to make it? Yeah, we got to have a negative in the exponent. So the simplest possible exponential decay function you could write is just output equals e to the power of negative input. H equals e to the negative t. So this would be an exponential decay function, but it's not the exponential decay function we want. What I would generally recommend doing, if you have a graph or at least a sketch of the graph, if you know the starting value and the asymptote you want it to approach, start by writing out just e to the negative t, and then figure out how to modify that to make it fit the graph. For example, if you just have h of t equals e to the negative t, what would be the asymptote of that exponential decay function? What's the asymptote of e to the negative t? What does that approach as time goes on? We want it to approach 54, but if we just have h of t equals e to the negative t, what does that function, that simple exponential decay function, approach as t goes on? Yeah, that's going to approach 0. So the default exponential decay function, e to the negative t, approaches 0. But we don't want it to approach 0, we want it to approach 54. So how do we modify a function to make it approach 54 instead? If the default exponential decay function starts at 1 and approaches 0, draw this more accurately. Yeah, we can add 54. If the default exponential decay function starts at 1 and approaches 0 as an asymptote, we can shift that, because really what we want to do is we want to take this default exponential decay function and shift it up 54 spaces so it's approaching 54 instead. We can accomplish that by just adding 54. But the other problem is we don't want it to be starting at 55 and approaching 54 from above. We want to stretch this so that it starts at 30 and approaches 54 from below. So how can we stretch or compress the graph vertically? What modifier to the function would have that effect of stretching and or flipping the graph? What other modifier could we attach to this function that would stretch or compress it vertically or flip it across an axis? Yeah, if we multiply it by something. So if we have some multiplier, I'm just going to write this as c for now because it's some unknown constant. So if we just fill in this unknown constant c, that's going to have the effect of vertically stretching it or compressing it, which allows us to match any initial conditions we want. And by the way, this multiplier, this times c, doesn't necessarily represent the initial conditions. It won't just be 30, but it can be found using the initial conditions. Before we find it though, what's one more modifier we could put in that would have the effect of stretching out how much time it takes to decay? How would you modify the graph to stretch or compress it in the t direction? Where could we put an extra multiplier that would accomplish that? Yeah, if we have some multiplier inside the exponent, which we would usually write as lambda. Let me grab a lambda here. Lambda. Okay, can you still see the problem all right? Okay. So some unknown constant c times e to the negative lambda t plus 54. The lambda represents something about how fast it decays, how long it takes to make that decay happen. And c represents something about the initial conditions, but won't just be 30. But now that we've got the general format, including the plus 54 to represent the asymptote, we can now start using information we have to solve for c and lambda. For example, to find c presumably has something to do with the initial conditions. At the initial conditions, what's the value of t and what's the value of h? Yeah, we know that when t equals 0, h equals 30. So we can fill in those values. If we just take this entire function, but we replace t with 0 and replace h with 30 centimeters, then we should now be able to solve for c. We do have two unknowns, c and lambda, but lambda times 0 is just 0, so we just get 0 in the exponent. And what's e to the 0? Yeah, e to the 0 is just 1, so we get 30 equals c times 1 plus 54. So what's c going to have to be? Yeah, c is going to be negative 24. So we can fill that in the function. C has to be negative 24. And what's important about that on the graph? What does negative 24 signify on the graph itself? I mean, the starting value was 30. Why did we get a negative 24 here? What did that represent? That's 24 away from what? Yeah, 24 away from 54. That negative 24 just means the starting value is 24 below the asymptote. And that amount below the asymptote is actually what's decaying. If you take a look at how far below the asymptote are you a little later, and a little later, and a little later, the distance from the asymptote is what's decaying. The value is increasing, but the distance from the asymptote is shrinking, which is why we call this exponential decay. It's getting closer and closer to the asymptote. Any questions on that so far? And it looks like we have one last unknown. We still don't know lambda. How could we figure out the value of lambda though? What's one more piece of information we have that we haven't used yet? Yeah, we have one more data point. We are told that by the problem that 23 minutes later, the depth is 53 centimeters. So we can use that as another data point. Fill in 23 for t, fill in 53 for h, and let's see what we get there. We know that when t equals 23, h equals 53. So if we fill that in using the function we have so far, if we replace h with 53 and replace t with 23, now what's the only unknown left? Yeah, so we can now solve this for lambda because that's the only unknown remaining. So how would we solve this for lambda? What operations would we have to do to get lambda isolated? Yeah, start by subtracting 54 from both sides. So we get negative 1 equals negative 24 times e to the negative lambda times 23, or just negative 23 lambda. And then what? Right, divide by 24. The negatives cancel, or divide by negative 24. Yeah, the negatives cancel out. So we get 1/24 equals e to the negative 23 lambda. And then what? Yeah, take the logarithm of both sides. And by the way, one thing that might be useful to do first, since we've got 1 over something, we've got e to a negative power, it might be useful to invert both sides first. If you raise each side to the negative 1 power, then the left side is just going to become 1 over, or just going to become 24 over 1, or 24. And the right side, a negative times a negative in the exponent becomes a positive. So e to the 23 times lambda. Not really a necessary step, but it's going to make the numbers easier to work with. Now we take the logarithm of both sides, natural logarithm. On the right side, logarithm and exponential functions cancel out, so we just get 23 times lambda. And then what's our last step here? Yeah, divided by 23. So lambda is logarithm of 24 divided by 23. And we can now fill that in to our exponential decay function. Negative t times logarithm of 24 over 23. And you could also punch that into a calculator and get a decimal approximation depending on how much accuracy you need. So if we type that into a calculator, we get logarithm of 24 in parentheses divided by 23, about 0.138. So about negative 0.138 times t. So there's our exponential decay function. This is a function that will produce exactly the graph we want. Any questions on that so far? So that's generally how I would recommend writing an exponential decay function. If you know it's going to be exponential decay, use the situation or analyze the situation somehow to figure out what's your starting point, what's your asymptote, and then you can write out an exponential decay function that has that starting point and that asymptote. The asymptote is going to be plus a constant outside the function. You can find the starting point by, or you can find the multiplier, the C value, by using the initial conditions. Just keep in mind that that multiplier doesn't really represent the initial conditions itself. It represents how far the initial condition is from the asymptote. At that point, the only unknown left should be the multiplier inside the exponential function, the lambda. You can find that by using one more data point if you have one, or alternatively, if you know the half-life or the time constant, you can find it that way instead also. And then once you got the equation, you can figure out all sorts of other stuff. For instance, part B, predict the depth of the water at t equals 12 minutes. Without actually running the numbers, how would you do that? How would you find the depth of the water after 12 minutes? If you want to know the depth of the water, that is the value of H after 12 minutes. Yeah, we could just plug in 12 for t. Because 12 minutes is a value of t, replace t with 12 minutes, punch this into a calculator, and that will tell you H, the height, 12 minutes after the start. And I haven't really been filling in units here, but the 0.138 should actually be in units of inverse minutes, 1 over minutes, so that when you multiply by minutes, it cancels out. And then the 24 and 54 are both in centimeters. We're in part C when it wants to know when will the depth be 47 centimeters. Mathematically, how would you do that? If you know the final depth is 47 centimeters, how would you figure out what time that happens? Right. Set H equal to 47, that's the final height, and then solve for T, which would be the only unknown, which would also involve eventually taking a logarithm. What about the half-life? How could you figure out the half-life here? Or what does half-life mean? That's the amount of time it takes for what to happen. Yeah, halfway between the initial value and the final asymptote. So one way you could do this is, well, what's halfway between the initial value 30 and the asymptote 54? Yeah, 42 is halfway between. So you could set H equal to 42 and solve for T. Or as a shortcut, if we were to set H equal to 42, we'd then subtract 54, divide by negative 24, and we would end up with the exponential part has to equal what fraction? If you set h equal to 42 and then subtract 54, divide by -24, what do you get? Yeah, that'll be 1/2. And so that will emerge naturally from the mathematics if you just set h equal to 42, the halfway point in between. But as a shortcut, you could just take the exponential part itself without the multiplier, without the plus the asymptote, just the exponential part and set it equal to 1/2. That's another useful way of thinking of half-life. It's the amount of time it takes for the exponential part to turn into exactly 1/2. So set the exponential part, e to the negative 0.138 times t equal to exactly 1/2. And then solve for t. Before we do that, though, once again, we've got e to a negative power equals 1 over something. So it would be a good idea to raise both sides to the -1 power and get e to the positive 0.138 times t equals 2 over 1, or just 2. And then what? How would you solve this for t? Right. Once again, take the logarithm of both sides, natural logarithm. And then one more step to solve for t. Yeah, divide by 0.138. So logarithm of 2 divided by 0.138 will be the half-life. Natural log of 2 divided by 0.138, about 5 minutes. And this will be in minutes because all the other times here are in minutes also. So that means it should take about 5 minutes, a little bit more than 5 minutes, to go halfway towards the asymptote. And then 5.023 minutes after that, at 10.046 minutes, it'll be halfway again. So 3/4 of the way towards the asymptote, and so on. Any questions on that so far? And as always, I would recommend looking at this. I mean, when you're talking about half-lives or time constants, think of it not in terms of the value, like 30. Think of it in terms of how far above or below the asymptote you are. Like you start off 24 below the asymptote. 1 half-life later, you'll take that 24 below and cut it in half. So you'll be 12 below the asymptote. 1 more half-life later, you'll be 6 below the asymptote, then 3 below the asymptote, then 1.5 below the asymptote, and so on. So the distance from the asymptote is really the value you're keeping track of in terms of half-life or time constant. Alternatively, for time constant, if we're talking about time constant, what do we want this exponential function to equal? Instead of becoming 1 over 2, we want it to become it's close to 1/3, really, closer to 1/3. But more specifically, it should be, 1 over e, exactly. So to find the time constant, set the e to the whatever, in this case, e to the negative 0.138 times t equal to 1 over e. In fact, 1 over e is the same as e to what power? Yeah, that's just e to the -1. Since we've got the same base, we can just set the exponents equal to each other. So a shortcut for finding the time constant is we can just say we want the time that turns the exponent into exactly -1. Divide by negative 0.138, and we get t equals 1 over 0.138. So that would be the time constant, 1 over 0.138. And how does that compare to the half-life? How are those related to each other? What's the only difference between those two expressions? Yeah, we just got this extra logarithm of 2 in the numerator. The half-life in general is going to be the time constant times logarithm of 2. Or in the other direction, if you know the half-life, you can divide by logarithm of 2 to find the time constant. So that's always going to be true. The half-life is always the time constant times logarithm of 2. But you could also find both of them individually by saying the half-life is the amount of time it takes for the exponential term to become exactly 1/2. The time constant is the amount of time it takes for the exponent, the stuff inside the exponential function, to become -1, so that the exponential function becomes 1/e. Any other questions on this so far? All right, then let's try a similar approach with that that capacitor example that I posted in the Discord earlier. Let me pull that up. And this one. Can you see this one all right with the circuit diagram? Okay, so here we've got a circuit assembled. The idea is we've got this 5 farad capacitor that has already been charged up. We're starting with a capacitor already charged with a positively charged plate on the bottom, 15 coulombs, and a negatively charged plate on top, -15 coulombs. So and in general, the 2 plates of the capacitor will have the same amount of charge but opposite signs. So we generally don't bother labeling both of them. We just label the absolute value of either one. So when we say charge equals 15 coulombs, we mean one of the plates has positive 15 coulombs, the other plate has -15 coulombs of charge. And that's how much charge this starts with. Presumably it's already been charged up by another battery somewhere else. We're now hooking that up to a 2 ohm resistor and a 9-volt battery and a switch. We haven't flipped the switch yet, but as soon as we flip the switch, current is allowed to flow. Any questions on that setup so far? And as usual, if we've got just a loop with a resistor, a capacitor, and possibly a battery, we should expect some sort of exponential decay. So just like with the previous example, anytime we're dealing with something we know is going to be exponential decay, I would recommend starting by looking at what's the initial condition and what's the final value everything's going to approach. In this case, we're looking at several values: current through the resistor and charge through the capacitor, or charge attached to the capacitor, stored on the capacitor, and also the voltages. But the thing is, if we can find current and charge, then that tells us everything we need to know about the voltages as well. Because in general, what do we know about the voltage of any battery? What should we expect the voltage of a battery to be? Yeah, that's just the EMF of the battery, the epsilon value. And that does not change. The important thing about a battery really is that its voltage does not change. So that's just going to be a constant plus epsilon. Delta V battery equals plus epsilon, and that's a constant. So we don't even need to know anything in order to graph delta V of the battery. We know it's 9 volts. We know that's not going to change. So what would the graph of delta V of the battery look like? If we're just graphing delta V equals 9 volts forever, what would that look like on a graph? Yeah, that's just going to be a horizontal line at 9 volts. Any constant function is just going to be a horizontal line. So we can already graph delta V of the battery without knowing anything else about the function or about the circuit. What formula could you use for delta V of a resistor, though? What does that depend on? Yeah, that's going to depend on current, specifically negative current times resistance. So that means if the current changes, the voltage of the resistor is going to change also. But if we can find a formula for current, we can just take that formula, multiply by R, and that'll be a formula for voltage of the resistor. Also, since R is just a constant, if you have a function, like presumably current is a function of time, what does a constant multiplier do to the graph of the function? Like if you have a function and you know the shape of its graph, and you multiply that function by 5, what would that do to the shape of the graph? Yeah, well, in this case, if you're multiplying by 5, it would actually stretch it out by a factor of 5. If you were multiplying by 1/5, it would compress it. But in general, a constant multiplier is just going to stretch or compress it in the vertical direction, but it keeps the same shape. So if you can find a graph of current, then the graph of delta V of the resistor will be the same shape, but just possibly stretched or compressed vertically, and also flipped upside down because of the negative. And what about the capacitor? Do you have a formula for delta V of the capacitor, or any capacitor? Yeah, charge over capacitance. And that's usually going to be negative charge over capacitance, although whether it's negative or positive kind of depends on which order you're subtracting it. And once again, C is just a constant multiplier. So charge over capacitance, the graph of that is going to look like the graph of charge, but with a vertical stretch or compression. So we really just need to find functions for charge as a function of time and current as a function of time. The graphs of voltage will be that same basic shape. Any questions on that so far? All right, then let's take a look at what's going on initially and also what's going on after a long time. And keep in mind, what we really care about is what's the charge on the capacitor and what's the current flowing through the resistor at each of those times. So to analyze that, let's say we're talking about at time 0. At time 0, do we know anything about the circuit? Does this tell us anything about what's happening at time 0? Yeah, we know the capacitor starts with 15 coulombs of charge. We've got to be careful about sign, though. The instructions here are to graph the charge on the upper plate of the capacitor. At time 0, what's the charge on the upper plate? Yeah, so we should write this as negative 15. Q of 0 equals negative 15. I'll call that just Q sub 0, since it's the charge at time 0. So the initial charge on the top plate is negative 15 coulombs. And can we figure out anything about the current flowing through the resistor? Or how would we find the current flowing through the resistor at time 0? Is there any way we could relate the current to everything else in the circuit? Not quite just epsilon over R, because the battery is not the only thing, in fact, not the only thing influencing the resistor here. Yeah, we're going to have something about the voltage of the capacitor also. And if you're not sure, you can always go back to the loop rule. In general, we should expect the sum of all the delta voltages in the loop to add up to 0. In this case, we just got 3 things that matter once we close the switch: the battery, the resistor, and the capacitor. So we'd have delta V of the battery plus delta V of the resistor plus delta V of the capacitor add up to 0. And of course, the order you add them together doesn't matter because addition is commutative anyway. If we fill these in, we know the battery is just a constant plus epsilon. The resistor is negative IR as usual. For the capacitor, we got to be careful about the capacitor. If you're talking about the clockwise direction, which is what we're defining to be the direction we care about here, as you go through each of these things, is the battery providing an increase or decrease in voltage? Yeah, it's providing an increase. We're going from low to high. And then what about the resistor? A decrease, yeah. So the resistor is going from high voltage to low voltage. And what about as we go through the capacitor in this direction? Is that providing an increase or decrease in voltage? Should we expect the higher voltage to be on the negative plate or the positive plate? Yeah, the positive plate is higher voltage than the negative plate. So if we start labeling voltages here, let me actually try labeling this with the color coding voltage map method we were looking at a long time ago. It looks like we have three different voltage zones here. We've got the voltage in this region, assuming we have closed the switch. We've got the voltage in this region, because the battery implements a change in voltage. The resistor also implements a change in voltage. So we've got another different voltage in this region. So it looks like we should expect three different voltages in this circuit. And we know from the capacitor, we know the negative plate is lower voltage and the positive plate is higher voltage. So if we start labeling those, the positive plate is associated with a high voltage. The negative plate is associated with a low voltage. But then we go through the battery, we get an even more of an increase in voltage. So from the high voltage zone, we're going to an even higher voltage zone. And then we go back to the low voltage zone. So the resistor is getting a voltage drop from very high voltage to low voltage. Since the capacitor in the clockwise direction, the capacitor is associated with an increase in voltage, we should treat that as positive. Strictly speaking, this is still negative Q over C. It's just that what's the value of charge right now? What value of Q are we assuming at time 0? Yeah, charge itself is a negative value. So if we actually fill these in, epsilon is plus 9 volts. Current is unknown, but we at least know the resistance is 2 ohms. And charge is negative 15 coulombs, the charge on the top plate. So we can still write voltage as negative Q over C. It's just that charge is negative 15. So negative 15 coulombs becomes positive 15 coulombs divided by the capacitance, 5 farads. Any questions on that setup so far? And if we simplify that, what's 15 coulombs over 5 farads? Yeah, 3, and specifically 3 what? What units do you get if you simplify coulombs over farads? Or what units should you expect it to be if it's a delta V? Yeah, that should be in volts. And coulombs over farad does indeed work out to volts. So we've got a plus 9 volts from the battery, a negative 2 ohms times current from the resistor, and a plus 3 volts from the capacitor. And note that the battery and the capacitor both have the same sign of voltage. They're both voltage boosts here, because as you're going clockwise, the battery causes an increase in voltage, and the capacitor also causes an increase in voltage. They're both pushing in the same direction. So they're both positive, both the same sign, which means we can combine those and get 9 plus 3, 12 volts plus negative 2 ohms times current. So the capacitor is acting with the battery in this case. Both of them are trying to push current around clockwise. And if you solve that for current, what do you get? Yeah, add 2 times I to both sides, divide both sides by 2 ohms. We get 6. And also the units there are going to be volts over ohms. What should that become? What should we expect current to be measured in? Yeah, volts over ohms is amps or amperes. So the current at time 0, I'll label that I sub 0, is 6 amps. So we now have all the information we need about the starting conditions, the time 0. We start with negative 15 coulombs of charge on the top plate, and we start with 6 amps of current flowing around the loop. Any questions on that so far? So we now have the initial conditions. What else should we need to figure out if we want to make an exponential decay graph? What's the other really important piece of information? We want to know where it starts. We also want to know what else. Yeah, the maximum, or well, it might be maximum, might be minimum, depending on whether it's increasing or decreasing. But in general, the asymptote that all of these are approaching. We want to know the asymptotic behavior or the end behavior. In other words, what's happening after a long time. That is, as t approaches positive infinity. As t approaches positive infinity, we want to know eventually, after a long time, how much charge is on the capacitor when it's full, and also how much current is flowing. If we wait for long enough, though, what should we expect the current to eventually be? Yeah, the current is going to approach zero, because we should expect eventually this will reach a steady state equilibrium, or at least approach a steady state equilibrium where the capacitor is as full as it's going to get. And if the current is still flowing, that means the capacitor is still in the process of changing. We're expecting the change to eventually die off, which means that the current will eventually be zero. So we can expect current final is 0 amps. And can we use that to figure out the charge on the capacitor? If we go all the way back to the loop rule, we can still reuse most of this. But what can we now plug in here? Yeah, we now know the delta voltage of the resistor is going to be 0 because the current is 0. If we just fill in 0 for current, we know there's no current flowing, because if the current was still flowing, the capacitor would be still in the process of changing. But we're looking for what it levels out to, what it will eventually be after a long time. After a long time, we can expect the current to have settled to a final value, which means no further change, which means no current is flowing. That gives us just epsilon minus Q over C equals 0. And we could even fill in the values. We know epsilon is 9 volts. We don't know the final charge, but we know the capacitance is 5 farads. If you solve that for Q final, what do you get? Not negative in this case, because we'd be adding Q final for 5 farads to both sides. Yeah, and then multiplying by 5 farads. So we would get positive 45 farads here. So that's the final charge, specifically final charge on which plate? Which plate are we treating as the value of Q here? Yeah, we've been assuming that Q represents the charge on the upper plate. So mathematically, this suggests the upper plate will end up with positive 45, sorry, that should be coulombs, positive 45 coulombs of charge. In other words, the signs are going to flip. The top plate is going to end up positive, the bottom plate is going to end up negative. And conceptually, the reason for that, if we imagine charge flowing out of the positive plate, we can imagine this as positive charge flowing out of the positive plate. Positive charge flowing from the positive terminal of the battery and accumulating on this plate. So we should expect positive charge to accumulate on the plate that's most directly connected to the positive terminal of the battery. We should expect negative charge to accumulate on the plate that's most directly connected to the negative terminal. So the negative charge on the top plate is going to have to dwindle and become less and less negative, eventually get to 0, and then become positive and more positive, approaching positive 45 coulombs. So we should expect the final charge on the capacitor to be positive 45 coulombs. In fact, in general, if you just got a single loop, including a capacitor and a battery, In the equilibrium solution or equilibrium result, you should expect the plate most directly connected to the positive terminal of the battery to end up with positive charge, and the plate most directly connected with the negative terminal of the battery to end up with negative charge. Of course, in the starting situation, it could be anything, depending on how it was set up in the first place. But the final situation is going to be pretty predictable. Any questions on those initial and final values so far?
So the initial value is -15 for the charge on the top plate of the capacitor.
Mhm.
And the final is 45. So the graph would go from -15 to 45.
Yes, this graph, the graph of charge when we graph it is going to have an initial value of -15 coulombs below the axis, and it's going to exponentially decay through the axis up towards an asymptote of +45.
Okay, thank you.
Mhm. And I think that'll become more clear when we actually draw out the graph. Before we draw the graph, though, there's one more important piece of information we want to get from here. If we just have the initial value and the asymptote, we can draw a rough sketch of the graph. But if we want more information about how much time it takes to decay, how quickly or how slowly it decays, what's one other piece of information we want to get out of this? Yeah, the time constant. And yeah, in this case, because it's just a simple loop, anytime you've got a single loop with one resistor, one capacitor, and optionally one battery, the time constant will always be resistance times capacitance. So we can use that. That's very predictable in these cases. The time constant is always resistance times capacitance if you just have this single loop. So that's 2 ohms times 5 farads, which will be what? And what units? If you multiply ohms times farads, what units of measurement do you get? If you actually write out those units, if we've got ohms times farads, if we go back to where those units show up in the first place, ohms was the resistance unit of measurement. So we've got volts equals amps times ohms. If you solve that for ohms, you get volts over amps. And then farads was the unit of capacitance. If you solve this for capacitance, you get charge over voltage. So that's coulombs per volt. So ohms is the same as volts over amps. Farads is the same as coulombs per volt. If you multiply those together, what's going to happen? Yeah, volts cancel out. We got volts in the numerator and volts in the denominator. So all that's left is 1 over amps times coulombs. But do you remember how amps is defined in the first place? What does electrical current mean? If we say the current is 5 amps, what does that actually mean? How do we define current? What's actually flowing? Yeah, charge over time. And we measure charge in coulombs. We measure time in seconds. So amps means coulombs per second. So 1 over amps would be the inverse of that, seconds per coulomb. So 1 over amps is seconds over coulombs. Multiply that by coulombs, and what happens? Yeah, coulombs cancel out. We're left with seconds. So the ohms times farads in resistance times capacitance naturally turns into seconds. So 2 ohms times 5 farads is not just 10, it's 10 seconds specifically. So that is the time constant. The time constant here is exactly 10 seconds. It'll take 10 seconds for the value to go to 1 over E of the way to the asymptote. In other words, about a third, about 37% of the distance from the asymptote. Any other questions on that setup so far? Okay, I'm going to transfer this to the marker board for the graphs because I think that's going to be a little easier to draw out, have a little more space. Moment. Okay, so for each of these graphs, and I've set these up with the same time axis. If we stack them up vertically, then we can use the same axis for time to make it easier to see what's going on at the same time. And for each of these, for instance, for charge, we want to start at -15. We want to approach 45, positive 45 as an asymptote. And we know it's going to approach asymptotically, exponential decay. But we might want a little more detail on how quickly it decays. Likewise, for current, we know it starts off at 6. And we know it's going to approach 0 as an asymptote. But again, we might want more detail on how quickly it decays. And let's also mark the voltages as well. For the voltages, we can mark the starting values and ending values. First of all, though, what do we know about the voltage of the battery? What was the voltage of the battery in this example? Yeah, that was a 9-volt battery. And it's just going to stay at 9 volts forever. So the graph of the battery is just going to be a horizontal line. And what about the capacitor? The capacitor started off with, or actually, let's do the resistor first. Delta V resistor is just the usual negative IR. At the beginning, the resistor had 6 amps of current, and that was a 2 ohm resistor. So we'd have negative 6 amps for the current and 2 ohms for the resistance. Multiply those together, and what do we get? Yeah, negative 12 volts. So the initial voltage of the resistor was way down here at negative 12. Resistor started at negative 12. And do you remember what was the initial voltage of the capacitor? How much voltage did the capacitor provide at the beginning? When we calculated charge over capacitance. Yeah, that was 3 volts. In fact, it was positive 3 volts because it was pushing in the same direction as the battery. So the capacitor started with 3 volts of voltage. So we have resistor and capacitor started at 3 volts. But we could also figure out their asymptotes. First of all, what do these add up to? 9 volts plus 3 volts plus negative 12 volts. Yeah, those add up to 0. And why should we expect them to add up to 0? Why should all those delta V's add up to 0? Exactly, this is the loop rule. The delta V from the battery plus the delta V from the capacitor plus the delta V from the resistor must add up to 0 because of the loop rule. Now the capacitor and resistor are going to be changing, but all 3 of them, the 9 volts from the battery plus whatever the capacitor is at plus whatever the resistor is at, have to add up to 0. So that's got to be the same sum. They got to add up to 0 volts at all times. If we take a look at their asymptotes, though, for the resistor, we know we're eventually approaching 0 amps of current, which means how much voltage will the resistor eventually approach? Yeah, the resistor is eventually going to approach 0 volts. And without going into too much detail about the amount of time yet, I'm just going to sketch this is going to approach like this. So we should expect exponential decay from -12 up towards 0 for the resistor. For the capacitor, we know eventually the capacitor has 45 coulombs of charge. How would we convert that into a voltage? Delta V for a capacitor should be what's our usual delta V formula for any capacitor? Yes, negative charge over capacitance. So going back to charge, the final charge was 45 coulombs, and the capacitance was 5 farads. So negative 45 coulombs over 5 farads. 45 over 5 should be 9. So negative 9 volts. So eventually the capacitor should be approaching a value of negative 9 volts as an asymptote. So that's our asymptote for the capacitor. The capacitor is going to be exponentially decaying towards negative 9 volts. And note that at the end, they still add up to 0. Positive 9 volts plus 0 plus negative 9 volts is still 0. So the loop rule still holds. In fact, at any instant in time, if you choose any instant in time, 9 volts plus whatever the capacitor is at right now, plus whatever the resistor is at right now, should add up to exactly 0. So that's what we should expect the voltage graph to look like. We could certainly add in more detail by introducing the idea of time constant and or half-life. But that should at least be the basic shape. Any questions on that so far? So with that out of the way conceptually, let's take a look at the charge on the capacitor graph and the current through the resistor graph in more mathematical detail. See if we can establish some more data points and some actual functions. First of all, the time constant I think would be a good unit of measurement to use. Like if we mark off the time graph in units of 10 seconds. So let's say this is 10 seconds, and then same distance further forward is another 10 seconds. And then same amount further forward is 30 seconds. And then we can mark the same instance in time on the current graph. And without even setting up the equation yet, we can get some data points using that idea of the time constant. For example, for the current graph, we start at 6. Exactly 1 time constant later, how would we figure out how much is left? How do you calculate how much is left after 1 time constant? Yeah, divide by E. 6, because we're currently 6 above the asymptote. After 10 seconds, 1 time constant, we divide by E. So 6 divided by E is about 2.2. So at this instant in time, we have about 2.2 amps remaining. One time constant later, what would we need to do? When we get to 20 seconds, that's 2 time constants have passed. After every time constant, what do you need to do? Yeah, we take that 2.2 and divide by E. Or alternatively, for more accuracy, you could start with 6 and you're dividing by E twice. So that means you're really dividing by what?
Like 20?
Sorry, what was that?
20?
20 is the amount of time. So we're not dividing by the amount of time. But if you start with some value and divide by E, and then take that value and divide by E again, overall, what are you dividing by?
Maybe E squared?
Right. Divide by E, that's the same as dividing by E squared. So one way you could do this all in one go is take the original value, divide by E squared, 6 divided by E squared, and I'm getting about 0.8. And then after 3 time constants, we could take 6 and divide by what?
E cubed.
Right, divide by e cubed, I'm getting about 0.3. So by doing that, just adding in these 2 more data points, we get a much better idea of how quickly this is decaying. In fact, we could get even more accuracy by also using not only the time constant, but what other important value of time. What's another important time? Yeah, the half-life. We could use the idea of half-life in addition to this to get even more data points and therefore even more accuracy on our graph. If we already know the time constant, 10 seconds from R times C, how do we turn that into the half-life? Right, multiply 10 seconds times logarithm of 2. 10 times logarithm of 2 is about 6.93. I'm just going to round that off to about 7, just to, because we don't really need all that much accuracy, about 7 seconds. So about 7 seconds is the half-life. So if I mark 7 seconds, and then also 2 half-lives would be 14 seconds, 3 half-lives would be 21 seconds. After 1 half-life, how much is left? We started with 6. 1 half-life later, how much is remaining? Yeah, 3 amps, half of the original. After another half-life, how much is left? Yeah, half of the 3 is 1.5. And you could also take the original amount divided by 2 squared, in other words, divided by 4. 1 half-life after that at 21, we should be down to half of that, so 0.75. Notice that that's just a little bit below the 0.8 here. So this gives us more and more and more data points, which gives us the ability to make a more accurate, smooth curve connecting them. So there's our exponential decay curve for current with a whole bunch of data points labeled. And you could always label more data points once you build the equation for it. In fact, let's go ahead and do that. Let's see if we can build the equation for this current graph. Starting with the idea of e to the negative something t. How do we make sure, well, first of all, it's got an asymptote of 0. So do we need to add anything here? No, if we don't add, I mean, if we did add anything, it would shift the asymptote. But the asymptote is 0, so we don't need any extra plus or minus anything. Which also means what multiplier should we have to get the correct starting value? Yeah, should just be 6. Or really 6 amps, because we should include units of measurement here. And you could think of that, once again, this multiplier could be thought of as the distance from the asymptote at the start. At the beginning, we are 6 above the asymptote, so this multiplier should be 6. We don't need any plus or minus anything because the asymptote is 0. And how do we decide this multiplier here? How does that relate to the values we've already got? The maximum value, actually in this case, the maximum value was 6. So that's really this multiplier here in this case. But more generally, if you had, let's say you had e to the negative lambda t. From this, yeah, this is ultimately going to relate to the time constant. Because the time constant is always going to be 1 over lambda. So to put it another way, lambda is 1 over the time constant. So that's going to be t over the time constant. In this case, time constant is 10 seconds. More generally, for an RC circuit, it'll be resistance times capacitance. So in this case, we can just say negative t over 10 seconds. So this should work just fine as a formula for current at any time. this is the function that goes with this graph. So we can say current as a function of time is 6 amps times e to the negative t over 10 seconds. And now that we've got the function, we can use this to predict the current at any time. If we wanted to know, for instance, the current at 25 seconds, we could just fill in 25 seconds for t, plug that into a calculator, and that'll tell us the current at that time. So once you've got the equation, you can get as much detail as you want by finding the data points for any time you want. And furthermore, we can now use that to find a formula for voltage, because how does the voltage on a resistor relate to the current flowing through the resistor? What's the usual formula for delta V of a resistor? Yeah, negative I times R. We have a formula for I, we just need to multiply that by negative R. So negative R, this was a 2 ohm resistor, times the current as a function. So negative 2 ohms times 6 amps becomes negative 12 volts. We still have times e to the negative t over 10 seconds. So this will be a formula for the voltage of the resistor at any time. Notice that that starts at negative 12 volts and decays towards 0 with a time constant of 10 seconds. So once you've got a function for current at any time, you can just multiply that by negative R to get a formula for voltage of the resistor at any time. And then you could also mark more points on that based on time constant and half-life if we want more accuracy on that graph. Any other questions on that so far? Then let's try the same approach on the graph for charge stored on the capacitor. And this is going to be a little trickier based on the fact that it's not approaching an asymptote of 0. And in fact, it even passes through the axis. It passes through 0. But we can still use the same approach. We just need to be careful about how we're describing things. If we look at this in terms of, let's say, in terms of time constant. At the beginning, the value is negative 15, but how far from the asymptote is that? Yeah, it's 60 below the asymptote. So we shouldn't really think of this value as a value of negative 15, even though it is. We should think of it as a value that's 60 below the asymptote. Imagine measuring everything from the asymptote itself. When we go forward one time constant, we're not taking the negative 15 and dividing by E. We're taking 60 below the asymptote and dividing by E. So if we take 60 divided by E, 60 divided by E is about 22. So that means one time constant later, we're not going to be at a value of 22, we're going to be at a value 22 below the asymptote. And what's 22 below the asymptote going to be? Yeah, 23. So after one time constant, at time 10 seconds, the value is 23 coulombs. And then if we go one time constant further forward, once again, we can divide by E again, or we can think of it as original divided by E squared. But that's the original being 60 below the asymptote. 60 below divided by E squared. We take 60 divided by E squared, we get about 8.1. So about 8 below. Again, that doesn't mean the value is 8, it means the value is 8 below the asymptote. What would be 8 below the asymptote here? Yeah, 37. So at time 20 seconds, we're going to be at 37. And then one more time constant, we can take the original 60 below, divide by e cubed, because it's been 3 time constants. 60 divided by e cubed is about 3. So 3 below the asymptote would be about 42. So we get a series of data points from this graph approaching closer and closer to 45. And we can do the same thing for time constant. The time constant is still going to be the same, or sorry, half-life is still going to be the same 7 seconds. Let's just do one half-life here, 7 seconds. We start 60 below the asymptote. What's half of that? Half of 60 below would be, yeah, 30 below. And 30 below the asymptote would be at 15. So after one half-life at 7 seconds, you're at 15 because you've gone halfway from negative 15 to positive 45. If we did take this to one more half-life, 14, you go halfway again. Currently, you're 30 below the asymptote. One more half-life later, you'll be half of that, 15 below the asymptote. 15 below 45 would be 30. So at about 14 seconds, a little less than 14, we were rounding off, you'd be at 30. And notice that these all fit into this nice exponential decay curve approaching 45. And again, you could fill in more data points if you want more accuracy, but I think that gives us a pretty good idea. And conceptually note what's happening here. We start off with negative charge on the upper plate of the capacitor. It's draining, it's discharging towards no charge, and then starts to build up positive charge instead. So the negative charge plate, the top plate, gets less and less negative charge until it's empty, but then it starts getting more and more positive charge because of the battery that's still attached to it. Meanwhile, the current starts off very fast and gets slower and slower and slower. Any questions on that circuit so far? There's one more bit of math here. Let's see if we can write an equation for this exponential decay graph. Charge at any time equals, to start with, we should expect an exponential decay function, so e to the negative something. And what's the something in this case? Based on the fact that it's still got the same time constant, the same rate of decay. Yeah, that'll still be negative t over RC, which is still negative t over 10 seconds. In fact, since this is just a single loop, everything's decaying together. Everything that's decaying is going to have a e to the negative t over 10 seconds in it. But in this case, we don't want the asymptote to be 0. We want the asymptote to be 45. So how do we accomplish that here? What change do we need to make to the function? Yeah, we would add 45, specifically 45 coulombs, because that's the unit of measurement for charge. So plus 45 coulombs gives us the right asymptote. And also we want to make sure we're starting at negative 15. So we're going to need some other multiplier here. Let's say times K, because we're already using C over here for capacitor, for coulombs. But what does that multiplier represent? We could just start plugging in values. We could plug in a value for T and a value for charge and solve for K. But what do you expect that multiplier to represent on this graph? Based on what you've seen in the previous expression, previous examples. Yeah, if we do plug in 0 for t, let's actually try that. If we plug in 0 for t, we just get k times e to the 0 plus 45 coulombs equals the charge. And what's the charge at time 0? Yeah, charge is going to be negative 15 coulombs. Notice though that this constant does not represent negative. It's not just going to be negative 15 though. It's determined by the starting value, but it is not the starting value itself. If you solve this for k, notice that e to the 0 is just 1. What do you get if you solve this for k? Yeah, K represents the amount below the asymptote. In this case, subtract 45, you get negative 60 coulombs. So K being negative 60 coulombs is because we're starting at negative 15, but the important thing is that's 60 below the asymptote. So the K value is talking about how far the initial value is from the asymptote. 60 below the asymptote means we're at negative 60. So K is negative 60 coulombs here. So this would be our complete equation for charge, the function of the charge graph. Negative 60 coulombs times e to the negative t over 10 seconds plus 45 coulombs. You could fill in any value you want for t and calculate charge at that time to get more and more data points on the graph. And you can always check that equation. If you're not really sure whether your equation is correct, you can always check by plugging in data points that you know the graph goes through based on given information or your calculations about half-life or time constant, and make sure that this equation makes those data points true. For example, we calculated earlier that at time 14 seconds, the charge should be 30. So you could fill in 14 for time, multiply this out, and make sure you get 30, or at least pretty close to 30. We were rounding off a little bit. But you can always check your function by trying out the data points and making sure it makes the equation true. Any questions on that charge graph so far, or the function we found for it? And again, if we wanted to convert that to a voltage graph, how do you convert charge on the capacitor to delta V of the capacitor? What's the usual formula for delta V of the capacitor? Yeah, negative Q over C. So we can just take Q, which is this entire function, including the plus 45, divide that by capacitance, which was 5 farads, I think. And what's left will be a function for voltage of the capacitor. And that will be the function that tells you this graph exactly. So this whole function, the whole thing, divided by 5 farads, gives you a function for this graph, the graph of voltage on the capacitor. Any other questions on that circuit example? Or capacitors in general, or exponential decay in general? And overall, just as one final thought on this, I think it's really important. Will voltage ever equal positive Q over C? It kind of depends on the order you subtract. In this case, we were specifically looking at Q as the value on the upper plate. I think you can always assume negative Q over C if Q represents the charge on the first plate you encounter. And then you take into account whether that charge is positive or negative. But if you're always using Q to represent the charge on the plate you first encounter as you're going along the loop, then I'm pretty sure that delta V will always be negative Q over C. If you're not sure, then try mapping out the voltages around the circuit and decide manually whether you should expect an increase or decrease in voltage, and then make it base it on that. Which graph were we working on? This function is specifically for this graph. Let me actually label that for the final result. Negative 60 coulombs times e to the negative t over 10 seconds, which is the same for all of these, plus 45 coulombs to give it the right asymptote. So the plus 45 coulombs constant determines the asymptote. The negative 60 coulombs multiplier reflects that the initial condition is 60 below the asymptote, and the negative t over 10 seconds describes how fast it decays. Specifically, the 10 seconds is the time constant, R times C. And generally, I would highly recommend not thinking of this in terms of memorizing a bunch of equations or memorizing a bunch of formulas. Think of it in terms of start with e to the negative t over whatever, or e to the negative t times whatever, and then figure out how do you have to modify that function to make it fit the graph you want. I would generally recommend, if you know something about the starting value and the final value, sketch out what you expect the graph to look like, especially the starting value and the asymptote. As long as you know those, you can build an exponential decay function that has that starting value and that asymptote. Imagine the asymptote as a vertical shift, so that's a plus or minus some constant. And then this multiplier is how far above or below the asymptote the starting value is. And if you forget that, you can always just fill in 0 for t and the starting value for whatever this is, and solve for that unknown multiplier. And then the exponent should just be negative t divided by the time constant, or negative t times lambda, however you want to write it. But again, even if you don't know the time constant, you can just treat this as a negative t times an unknown multiplier, fill in one more data point that you have on the graph, if you have one more data point, and solve for lambda as the last unknown. In fact, in general, if you can write out a function except for one last unknown parameter, then you can fill in one data point for t and whatever, the variables, and then solve for that last unknown parameter. You could even take that a step further. If you have two unknown parameters and you have two data points, you can fill in each of those data points and get a system of two equations, two unknowns. More generally, as long as you have as many data points as there are unknown parameters in the function, then it is possible to solve for those parameters. It just becomes more and more difficult the more unknowns there are. So ideally, it's best to narrow it down to just one unknown and then solve for that. Any other questions on exponential decay? If it's discharging, I would generally still write it as delta V equals negative Q over C. As long as I think as long as you're treating Q as the charge on a plate, the first plate you encounter in the loop rule, then that should work. And ultimately, the reason why there's a negative there, the negative here represents the fact that the voltage from the capacitor, the push from the capacitor, is attempting to remove charge from itself. If you think of positive as the direction of putting more charge into the capacitor is always pushing back against more charge being put into itself. Or if it's discharging, it's pushing to push charge out of itself. So the delta V of the capacitor is always attempting to remove charge from itself, or at least prevent more charge from entering itself. So that's what the negative sign here really represents conceptually. Any other questions on capacitors or exponential decay? Then let's take another look at this Newton's law problem that somebody sent earlier as well. One moment. Here we've got a scale with 3 heavy chain links hanging from it. And we know some information. We know the mass of the top link, we know the mass of the bottom link. We don't know the mass of the middle link, but we at least know the force of the top ring on the middle ring is 25 newtons. And we're trying to figure out, first of all, drawing a force diagram for each one of these. One moment. When the problem says the system is in steady state, steady state doesn't really tell you anything about the delta total head, the delta total energy density. Steady state just means nothing is really changing as time passes. So maybe there's current flowing, but it's flowing at a constant rate. The current isn't changing as time passes. And maybe there's a pump, but the pump is pushing the same amount as time passes. So not a steady state would be something like where the current is changing as time passes. Like maybe you've got water draining out of a tank, and the more it drains, the slower it gets. Or for instance, any circuit with a capacitor that's changing as time passes, that would not be a steady state. Steady state just means that it's not changing significantly as time passes, or maybe any changes that were going to happen have already happened. Everything is already balanced out. But stuff could still be moving. There could still be losses in energy density due to current and resistance, for instance. In this one, though, let's try drawing out the force diagrams for each of these. If we take a look at each one of these chain links individually, top, middle, and bottom, I don't think we really need to worry about torque here. There's not really any rotational stuff going on. So we should be able to just treat each one of these as a single point. So if we take a look at the top link, middle link, and bottom link, then I think we should be able to analyze the forces on each one. And of those, top, middle, and bottom, which one do you think is going to be the easiest to analyze? Yeah, the bottom link I think is going to be easiest because what are the only forces acting on the bottom link? We've got gravity pulling it down, and how strong, well, probably want to make the arrow smaller than that. How strong is the force of gravity on the bottom link? I'm going to call it FGB for force of gravity on the bottom link. How strong would that force be? Yeah, 10 newtons. And I would say 10 newtons in the downwards direction. Its y component would be negative 10 newtons, but the magnitude of the force is 10 because magnitude is absolute value. So we've got 10 newtons of force pulling down. In fact, let's go ahead and fill in gravity on all three of these. What's force of gravity on the top link? How strong would that be if we know its mass is 1.4 kilograms? Yeah, 1.4 kilograms times approximately 10 meters per second squared would be 14 newtons in the downwards direction. And for the middle link, we don't know its mass, but we can at least write its force of gravity as G times the mass, 10 newtons times the mass. So 14 or 10 meters per second squared times, I'm going to write this as capital M as the unknown mass of the middle link. But of course, those aren't the only forces acting on them because they're not falling. Again, starting with the bottom one, because I think that's going to be the simplest one to analyze. What's the one other force acting on the bottom link that prevents it from falling?
The force of the middle link?
Yeah, the middle link is exerting a force on the bottom link, pulling it up. So I'm going to call that, that's the force of the middle link on the bottom link. So let's say force of the middle on the bottom. And how strong does that have to be?
Ten newtons in the positive direction?
Yeah, 10 newtons upwards, because we know, why do we know these have to balance each other out? Why would these have to add up to 0?
It's not moving.
Yeah, well, not only not moving, but not what? Remember, force doesn't cause motion. What does force cause?
It's not accelerating.
Right, the acceleration is really the important part. As far as forces are concerned, it doesn't matter one bit whether the object is moving or not. What matters is the object accelerating or not? It's possible to be moving without accelerating if you are moving at a constant velocity. It's also possible, at least for an instant, to be accelerating without moving. Like let's say you've got an object that was thrown upwards. It slows down, comes to a stop, and falls back down. At the top of its flight, what's its velocity?
0.
Right. At that instant, it's just hanging there for one instant and its velocity is 0. But what's its acceleration at that instant? It's still being pulled by gravity, right? It's still in free fall. So what's the acceleration caused by gravity alone?
Would be 9.8 meters per second squared.
Right. So at that instant, at the top of its flight, its velocity at that instant is 0, but it's still experiencing this downwards acceleration of 9.8 meters per second squared, or about 10. So it's possible, at least for that instant, for the object to have 0 velocity, not moving at that instant, but it is accelerating. So don't trust the idea of just motion alone. The important thing is if the acceleration is 0, then you know that the total force must be 0. So acceleration is really what to watch for. Total force causes acceleration. No acceleration means 0 total force, which is the case in this situation. However, note that in part D, we're assuming that the whole system is accelerating. So that would change the forces. The forces would not add up to 0 in that case. But in this situation, we're assuming no acceleration. Therefore, the forces have to add up to 0. And if we know the middle link is exerting a 10 Newton upward force on the bottom link, what else has to be happening according to Newton's third law? If the middle link is pulling the bottom link up, what's the bottom link doing to the middle link?
Has to be pulling it down.
Right, and pulling it down with how much force?
10 newtons.
Right, we're going to have a 10 Newton force from the bottom link on the middle link. So the force of the bottom link on the middle link is also 10 Newtons, but in the opposite direction. These are the equal and opposite forces that Newton's third law is talking about. We would describe these as a third law pair. So this force and this force, that's the pair of equal and opposite forces, the action and equal and opposite reaction that Newton's third law is talking about. Forces come in pairs, force of object 1 acting on object 2, and force of object 2 acting on object 1, that are same strength but in opposite directions. And so far, that's just a bunch of downward force on the middle object, the middle link. What's holding it up? Why is the middle link not falling? Yeah, the top link is holding it up. So we've got an upward force of the top link on the middle link. So we'll call that force from the top on the middle. And in this case, that's not unknown. That actually is provided. It tells us we know that the force of the top ring on the middle ring is 25 newtons. So that's actually given information. And it looks like those are all the forces acting on the middle link. So what can we now figure out? What unknown can we now find? Yeah, we know that these three forces have to add up to 0 because the middle link is not accelerating. So 25 up plus 10 down plus some unknown down is 0. If you solve for that missing force, you find that it's 15 newtons downwards. Because that way we got 25 up, 10 and 15 down, those balance out to 0. And that also tells us, what does the mass of the middle link have to be? We've got 10 times an unknown mass equals 15 newtons. What's that unknown mass?
1.5 kilograms.
Yeah, middle link has to have a mass of 1.5 kilograms. So we now know the mass of that middle link. And I think then the top link we can now analyze as well, because we've got a 14 Newton downward force. And also, what other force is it experiencing from the middle link? Yeah, the top link is exerting a 25 Newton upward force on the middle link. So by Newton's third law, the middle link is exerting the exact opposite of that, 25 Newtons downward force on the top link. So the top link is experiencing 25 Newtons force downwards as the force from the middle link. So that's the force of the middle link on the top link, which is 25 Newtons downwards. By the way, is the bottom link exerting any force on the top link? Are they in contact with each other? No, the bottom link is not physically touching the top link. There's no physical contact, and that means there's no contact force. The bottom link and top link cannot exert any normal force or friction force or tension force on each other because they're not in physical contact. They're not actually touching each other. They could hypothetically exert remote forces, long distance forces, like electrical or magnetic attraction and repulsion or gravity. But this doesn't say anything about charges or magnetism, and they're definitely not massive enough for gravity to play a significant role on each other. So I think we can assume that the bottom link and top link do not exert forces on each other. The presence of the bottom link does influence the force the middle link exerts on the top link. Like the reason why the middle link is exerting exactly 25 newtons of force on the top link is related to the presence of the bottom link. But we wouldn't have a force from the bottom link on the top link because they're not touching each other. However, what other force is acting on the top link to prevent it from falling? What's holding it up?
The scale?
Yeah, we've got an upwards force on the top from the scale. And that's actually going to have to be pretty big, because what does that have to balance out?
The 39 newtons down.
Right. If we've got 39 newtons total of downwards force, we need 39 newtons of upwards force, so the actual total is 0. So the force of the scale on the top link is going to have to be 39 newtons upwards. Which means, what's the scale experiencing? If we were to draw out, and I hadn't drawn it here, but it does ask draw a free body diagram for the scale itself. What forces is the scale going to experience? First of all, just from Newton's third law, what force do we have to include to keep everything honest? If the scale is pulling the top link, yeah, if the scale is pulling the top link up, then the top link has to be pulling the scale down with the same 39 Newton force. So these two would be a third law pair. You've got the force of the scale pulling the top link up with 39 newtons, and you've got the force of the top link pulling the scale down with 39 newtons of force also. So those would be a third law pair that we need to include. But again, the scale is not falling either. So what's holding the scale up?
The ceiling?
Yeah, the ceiling itself is exerting a force. Presumably the scale is attached to the ceiling by a rope or another hook or something. So we would have an upward force from the ceiling on the scale. And how strong does that have to be?
$39 newtons.
Right, because the scale is not accelerating. And it is, we can ignore gravity here because it says neglect the mass of the scale. We're assuming the mass of the scale is so small compared to the others that it can be just ignored. So we can treat that as just the scale is being pulled down by the top link and being pulled up by the ceiling, and those have to add up to 0. So 39 and 39. Well, 39 up and 39 down. And that means what's the scale's display going to be? What number is the scale going to say if it's been calibrated correctly?
39 newtons?
Yeah, the scale should say 39 newtons, because the whole point of a scale is to measure how much force it's being pulled with, not the total force, but just the force from whatever it's attached to. And of course, the ceiling is going to apply the same amount of force so that the scale doesn't accelerate. But the spring within the scale does stretch because it's got this tension force pulling on it. And how does that compare to the total mass of everything hanging from it? What is that total mass? Now that we know the mass of all of them. Yeah, 3.9 kilograms. So what is the 39 newtons supposed to be describing here? What does that tell you about the object, the total object, the 3 links?
They have a total mass of 3.9 kilograms.
And so what is the 39 newtons telling you? How does that relate to the total mass? What is a scale actually measuring?
The force of gravity on an object.
Or I would say the total weight. In other words, 3.9 kilograms, the mass, times the acceleration of gravity. And by the way, the scale is not directly measuring the force of gravity. It's not like the scale has some magic gravitometer or something that can directly measure the force of gravity on some other object. What force is the scale actually experiencing here that it's describing as 39 newtons? Because notice that the force diagram for the scale doesn't include gravity at all. Yeah, what the scale is actually displaying, the 39 newtons is really the force from the top link on the scale. So that's really what it's measuring. It's measuring the force it has to exert to hold that up. That so happens to equal the total weight of these three rings, but only because we're assuming this is not accelerating. If in part D, if this whole thing is in an elevator that is accelerating, that's going to change things. And to figure out how it changes, I would go one step at a time, starting from the bottom and working your way up again. To begin with, if the whole thing is accelerating downwards with 2 meters per second squared, how would that change our calculations? What assumption would we have to modify? For instance, what were we originally assuming about these two forces that's no longer going to be true? Yeah, the net force is no longer going to be 0. We can calculate what the new net force is. We can say the new net force on the bottom link will be, how would we calculate the new net force? Yeah, once again, we can use mass times acceleration, Newton's second law. Previously, we were essentially using Newton's first law, that no acceleration meant 0 net force. But now that it is accelerating, we use Newton's second law, that the actual net force is going to be mass times acceleration. Specifically, mass of this one object, 1 kilogram, times its acceleration, 2 meters per second squared, because the whole thing is accelerating at 2 meters per second squared. So 1 kilogram times 2 meters per second squared would be 2 newtons, specifically 2 newtons downwards. So we need these forces to add up to 2 newtons downwards instead of 0. Of these, which one can actually change? Or to put it another way, is there either one of these that we know is not going to change just because we put this in an elevator? Yeah, force of gravity is not going to change. That's always going to be mass of the object times acceleration of gravity. And mass isn't changing, and the acceleration of gravity doesn't change unless you move to a different planet, or move like really high up in elevation or really low in elevation. So we assume the force of gravity does not change. This still has a true weight of 10 newtons. But it's the contact force with the middle link can change based on how tightly it's stretched. So what does the contact force from the middle link now have to be in order for the total force to now be 2 newtons downwards? Yeah, this is now going to be only 8 newtons. The normal force from the middle link is going to be weaker. It doesn't have to pull as hard because the bottom link is now accelerating downwards. It's not truly in free fall, but it's kind of in partial fall. It is accelerating downwards, so the middle link doesn't have to pull up as hard. And that also immediately modifies the corresponding Newton's third law pair. Force of the bottom link on the middle link is also now going to be 8 newtons because those have to be equal and opposite. And of course, its weight doesn't change because gravity hasn't changed at all. We just have a weaker normal force. But that's also going to change the force of the top link on the middle link. That will also change. Force of gravity still 15 newtons. We're not changing how strong gravity is. But what does the new F net have to be on this middle link? How would we calculate that? We've got 1.5 kilograms of mass. What is this acceleration going to be? What is this whole thing accelerating at? Yeah, the whole thing is accelerating 2 meters per second squared downwards. Once again, we can multiply mass times acceleration to get the total force. And what is mass times acceleration here? Yeah, 3 newtons downwards. 1.5 kilograms times 2 meters per second squared downwards is 3 newtons downwards. So we need these forces to add up to 3 newtons downwards. We've got 15 newtons downwards worth of gravity. Can't do anything about that. 8 newtons downwards from the bottom link because of Newton's third law. So what does the new force from the top link have to be to make these add up to 3 newtons downwards? If we've got 8 and 15, that's 23 downwards so far. How much upward force do we need to balance out the 23 downwards to get 3 downwards overall? Yeah, 20 newtons upward should work. If the new force is 20 newtons upwards, 20 newtons upwards plus 23 newtons downwards is a total of 3 newtons downwards, which is exactly what we need. So that suggests that this force has gotten weaker also. We now have a weaker upward force from the top link. And we should also modify the corresponding Newton's second law, or Newton's third law force, the third law pair. The new force from the middle link on the top link is 20 newtons. We need to modify that to match. So that has gotten weaker. And also, what should we expect the new net force on the top link to be? If we multiply that mass times the acceleration. Yeah, 1.4, wait, what's 1.4 times 2? Yeah, 2.8 newtons down, 2.8 newtons in the downwards direction. So we need these to add up to 2.8 newtons downward. If we take a look at just the downwards so far, we got 14 plus 20 is 34. How much upward do we need so that that plus 24 or 34 downwards is 2.8 overall? If we think of these in terms of components, we've got positive something plus negative 34 equals negative 2.8. What would that something have to be? Yeah, 31.2 newtons upwards. So that has also gotten weaker. All of these forces, except for the gravitational forces, have gotten weaker. So what is the scale actually going to display then? What's the force on the scale from the top link? Yeah, that's going to be 31.2 newtons downwards. Because once again, that's a third law pair. The force of the top link on the scale is equal and opposite to the force of the scale on the top link. Uh, 2.8. It needs to balance out not only the 20 newtons from the middle link, but also the 14 newtons from gravity. So gravity on the top link plus the middle link's force on the top link, that's a total of 34 newtons downwards. So we need 31.2 newtons upwards so that the total is still 2.8 downwards. Or if you look at it in terms of components, you've got 14 newtons downwards plus 20 newtons downwards plus some unknown equals 2.8 newtons downwards. So this would be the equation you're solving in terms of just the y components. 14 downwards, 20 downwards, and some unknown amount upwards equals 2.8 newtons downwards. Add 34 newtons to both sides, you get 34 minus 2.8, which is 31.2. So that'll be the new force of the spring on the or force of the scale on the top link. Likewise, the new force of the top link on the scale. And the force on the ceiling is also going to get weaker because that has to just hold up the scale. So this will also be 31.2 newtons. So all these forces, except force of gravity, are getting weaker as a result of this acceleration. And that means the scale is now going to display, instead of 39 newtons, it now displays 31.2 newtons. Does that mean that this chain has gotten lighter? Has gravity gotten weaker in this region? No, all the forces of gravity are still the same. The total weight, the true weight of the chain is still 39 newtons because gravity hasn't changed at all. But the scale is displaying a weaker apparent weight because the system is accelerating. So the number displayed on the scale can only be trusted as the actual weight of the thing hanging from it if the system is not accelerating. If the system is accelerating, then the scale might show a heavier or lighter apparent weight as a result of that. But the thing is, it's not just the scale. If you're holding this, it's going to feel lighter, and you're going to feel lighter. Everything's going to feel lighter because all those forces except gravity get weaker. And you can't directly feel the force of gravity. If you're just standing on a floor, you're not really feeling the force of gravity. You're feeling the force of the floor holding you up. If you're in a room that's accelerating, you might feel heavier or lighter because the floor would be applying more or less normal force than your actual weight. So when we talk about weight, true weight means the force of gravity on the object or on the system of objects. But the apparent weight, which for most practical purposes is what actually matters, would be the force that the scale actually displays. And that might be lighter or heavier than the true weight, depending on whether the system's accelerating in the same or opposite direction. For instance, if this whole system was accelerating upwards, I would expect the scale to display something larger than 39 newtons. But generally, you can find that by going through the sequence of force diagrams, usually starting with whatever object is going to have the least forces acting on it, or the most predictable forces acting on it. Start with whatever's simplest, work your way from there until you figure out all the forces. Any other questions on that? All right, well, that's all the time we got for today. So good luck on finals. Have a nice break, and I hope to see you in Physics 7C next quarter.
Thank you.
You're welcome.